Thank you, Kevin, for that introduction. Again, hi, my name is Chia-In Lin. Today I'm going to be talking to you about a method that my group uses to create diagnostic tools for various diseases. Specifically, my project looks at a pregnancy-related disease called preeclampsia. So preeclampsia affects 5 to 8% of pregnant women and is the cause of 18% of maternal deaths in the US alone. Clinical symptoms of preeclampsia are hypertension and excess protein in the urine. Advanced conditions of preeclampsia are hemolysis, elevated liver enzyme, and low platelet count, or HELP syndrome, or the mother can succumb to seizures. The only treatment available for preeclampsia is to prematurely deliver the baby. So currently, the pathogenesis for preeclampsia is poorly understood. Through in vitro and in vivo studies, it was shown that AT1 autoantibodies are able to present the symptoms of preeclampsia using mouse models. However, later studies showed that AT1 autoantibodies are a poor diagnostic tool for preeclampsia because the clinical test is lengthy and complicated, and also because of their presence in normal outcome pregnancies and other diseases such as systemic sclerosis and kidney transplant rejection patients. So we hypothesized that there are other antibodies that are specific to preeclampsia that we can use as an effective diagnostic tool for preeclampsia. So to do this, my project is twofold. The first part is to explore fluorescent signal by altering the peptide density on the cell surface and the concentration of antibodies in solution using a model antibody peptide interaction. With the model antibody interaction, I will be looking at 2 different peptides. The second part of my project is to measure the accuracy of one particular peptide's ability to differentiate between preeclamptic patients and normal outcome pregnancies. So the overall method for my project is to express peptides on the cell surface of the bacteria, then incubate them with fluorescently tagged antibodies, either the model antibody or the patient antibodies. And then using flow cytometry to force the cells into a single file line, we can use a laser to measure the fluorescence intensity of each cell. So let's start at the beginning of this process. So here we have an E. coli cell that is expressing the peptide reagent. The E. coli cell is used solely as a support vector to express our peptides and contributes nothing in terms of the disease. So taking a closer look at the cell surface, we have the peptide, which is the pink triangle, attached to a scaffold which floats within the cell membrane. Our negative control in this case would simply be the scaffold without the peptide. So after taking the peptides and incubating them with the antibodies, the structure looks something like this. So with the model antibody, we have the peptide, which is bound to the model antibody. The model antibody is conjugated to a small molecule, which binds to a fluorophore, allowing this entire structure to fluoresce. For the patient antibody, we have the peptide, which binds to the patient antibody, either the preeclamptic patient or the normal patient. Then we have a secondary antibody, which binds to the patient antibody. The secondary antibody is bound to the same small molecule you saw in the model antibody structure, again binding to a fluorophore, allowing this entire structure to fluoresce. So let's start off by looking at some data for the model antibody interaction. So here's a graph of the induction time, or the time taken to allow the peptides to be expressed on the cell surface, versus their fluorescent intensity. Again, as kind of a reminder, I looked at 2 different peptides, and while peptide B has a lower overall fluorescent intensity than peptide A, you still see this general trend of a positive correlation between the induction time and the fluorescent intensity. So this graph is of the antibody concentration versus the fluorescent intensity. Again, you see that there is a positive correlation to this sigmoidal curve showing that the antibody concentration is positively correlated to the fluorescent intensity. What you might not see is that the peptide density affects the apparent binding affinity between the peptide and the antibody. So as the equilibrium dissociation constant, or EDC, goes down in value, the strength of the apparent binding affinity goes up. So for the dotted lines, you see that the EDC values are less than the EDC for the solid lines. And that means that the 60-minute induction time has a stronger binding affinity than the 30-minute induction time. So here we have, so the graph on the left shows the fluorescent fold, or how much each patient sample fluoresces over the background. The graph on the right is simply a sample of all of the patients I tested to show that I performed repeat analyses. So these black lines indicate the average of both of these distributions. If we were to draw a line where the average for the normal distribution is, like that, we can say that these patients above the cutoff have preeclampsia. After performing 2 different statistical tests, we can say that our preeclamptic patients have a significantly different reactivity than the normal outcome patients. So for those of you who are unfamiliar with this curve, this is a receiver operating characteristic curve, or a ROC curve. And its purpose is to tell us the overall diagnostic use of our peptide. So the curve is generated by having multiple fluorescent cutoffs and determining how many preeclamptic patients fall above the cutoff and how many normal outcome patients fall below the cutoff, thus giving it this stepwise shape. So the part that tells us the overall diagnostic use of the peptide is the area under the curve. So if we have an area of 1, as with the dotted blue lines, that tells us that we have a perfect diagnostic. Whereas if we have, an area of 0.5 or less with this red dotted line, that tells us that we have a diagnostic that is unacceptable by clinical standards. So for my ROC curve, I generated an area of 0.7, which is a fairly high diagnostic. Another characteristic of this curve that we want is to find a fluorescent cutoff that tells us, or that gives us the best diagnostic, or basically a point that is as close to the upper left corner as possible. So in this case, this point gives us the best diagnostic, which is 65% of the preeclamptic patients who are correctly diagnosed with preeclampsia. And if you do the math, 85% of the normal patients were correctly diagnosed with normal outcomes. So from the model antibody interaction, we found that there is a direct correlation between the peptide density and the fluorescent intensity. We also found that the peptide density affected the cell surface binding affinity between the peptide and the antibody. And from the patient antibody studies, we found that the area under the ROC curve gave us a fairly high diagnostic for the peptide I was testing. So what can we expect for future preeclamptic patients? So the peptide that I was testing came from a larger set that my mentor previously characterized. And looking at the similarities between the peptide that I tested versus the peptides that she had already characterized, we can compare those similarities with protein databanks. And hopefully we can find a native antigen that can be used for possible therapies for preeclamptic patients, thus reducing the number of maternal deaths and premature births overall. So I'd like to thank my mentor, Sarah Elliott, for her infinite patience with me. I'd also like to thank Dr. Patrick Doherty for allowing me to work in his lab, and CSET for awarding me the EUREKA internship and giving me this opportunity for research. Thanks.